So little portion we had not covered last time about the particulate formation, but you can still go back to slides. Those I'm sure will be loaded by today. Okay, then you can have a look, but I want to quickly move to something else, that is about the atmospheric chemistry. You remember we have been talking all through that in the sense that we have three things, S, T and R. Okay, source, transport and receptor. Okay, we will be just working back and forth. Okay, and so we want to quickly do about the atmospheric reaction as to once the pollutants are in the atmosphere, what can they do? Can they do good things? Can they do the bad things? Or they may not do anything. Okay, but we are talking more of the chemical transformation of the pollutants. Okay, and that depends on many things, but we will try to go as much as we need to go really. But atmospheric chemistry can be a big subject in itself. Okay, so but we won't go that far because we like to cover something like in 2 to 3 lectures. And then when we look at the atmospheric chemistry, and what's important that again it can affect the people, it can affect the receptor, and then it can affect sometimes in the positive sense, because atmospheric chemistry can not only create problems and serious problems, it can also sometimes reduce problem because they are able to scavenge out the pollutants, scavenge out the harmful things and can produce something very benign or not so harmful. Okay, so there can be positive effects. Of course, it affects the stratospheric ozone which is being formed in the stratosphere all the time. That is a good thing. And then it can also remove some of the toxic substances from the atmosphere, for example, the OH radicals or the other things. Okay, negative effects in the they can produce a substance which is sometimes more harmful, deadlier and more problematic. For example, ozone, as I said all the time, when you talk about the troposphere, ozone is a pollutant. Ozone should not be there because we don't need ozone in troposphere, but it is formed. So none of the processes generally, by and large 99% processes do not release any ozone, but ozone is formed where? In the atmosphere, troposphere, and that becomes a problem. Okay, and this is a worldwide problem. In fact, lots of efforts are on to measure and to be able to map the ozone, through the satellite, and NASA is trying very hard. Then which areas are more polluted in terms of the ozone, where the more ozone is formed and things like that. And then because ozone can damage the human, animal, plants and buildings. Okay, well, not necessarily the buildings, but in some sense, like indirectly it can produce, it can help produce acids which can destroy the buildings as well. Indirect effects, the climate change system, we know it is can affect the climate. Both the particles can affect the climate, the gases can affect the climate. For example, methane, we all know the effect on methane in terms of the greenhouse gases. Okay, we can also know that some of the particles are formed in the atmosphere, that we saw how the volatile organic carbon compounds, like because of their vapor pressure are high, supersaturated, and it condenses. In fact, some of the atmospheric reaction can also form the particles, not only through the organic route, we can also form the particles from the inorganic routes. And that's why sometimes we wonder that while we are controlling lots of pollution at the source of the particulate matter, we are cleaning the chimneys, but still we find the particles to be there. And those particles many of the particles are formed in the atmosphere from the precursor gases. Okay, so we control the particle, we are very happy, our chimney looks fine. And they say, well, we have control, but when we go and measure outside, we still get the particles that had originated or that had not originated, but they were formed in the atmosphere from the gases. Those had originated from the source. So that's little thing. So unless we understand this mechanism, the science, the chemistry, we can't manage the air pollution. So there are indirect effects also. Sometimes so much of the nitrogen species can also be downwashed, and it can affect even the ecosystem and can add to the eutrophication. With this background, let's get to something more serious. Okay, these are the issues which somehow we should be able to answer once we know the chemistry and how has atmosphere composition changed over the time. What is the human contribution to this change? Because something occurring naturally, there is little we can do about that, because the sizes of nature's operation sometimes can be very large and we have no control. For example, something is changing because of the volcanic activities. What can we do? I mean, there is nothing that we can go and stop volcano. But something what we do, we can certainly control that, and we should try to control that. Okay? Because the natural sources can also be interesting. Some of you remember the presentation from Dr. Ravi Kant, what was his name, last name I forgot. Pathak, yes. And he did say how the trees can pollute in terms of the organic vapors and organic things that can come out. And you remember that he also said those vapors in presence of seeds like ammonium nitrate, sulfate would produce more particulate, right? You recall that? Okay. So, nature can also play, and sometimes to handle nature could be difficult. What is the human contribution? How will the atmospheric composition change in future? How the atmospheric composition change affect ecosystem, economies, and the quality of life? Like that can be another thing. But we will stay more or less with the science. But the implication of science is essentially to answer the questions that are being raised here. Okay. Atmospheric chemistry fundamental, we know about the atmospheric composition, the basic ingredients of atmospheric chemistry, very important to understand as to what happens, chemical reaction in the atmosphere. We have to understand chemical reaction kinetics, we have to understand the conditions under which things can happen. Temperature is very fundamental to many of the reactions. The temperature is important, the humidity is important, and above all these things, what do you think is important? Where is all energy that will come from to break and to, like we need energy all the time, and then energy comes from the sun. Okay, the sun will bring a lot of energy. So you will see, we will talk a lot about the sun's energy that is coming in. In fact, the atmosphere in terms of the pollutants could look very different in the day, in the night it could be different. And on the day when it's very heavily overcast and you're not getting enough of the sun, and you may find the atmosphere look very different. Okay, and so since if you know the knowledge, if you have the science with you, then you can explain these numbers. Okay, so that's what is very important to understand the science. This is something we did last time. We tried to define the ppm by volume, that is the 10 to the minus 6 mole per mole of the gas versus the air, and ppb will be the nanomoles per mole, and this is the picomoles per mole, that will be the ppt, that's parts per trillion. That we had done last time, so we'll quickly skip this thing, go on to something else. And now at least these are the things which we'll talk. Let me again tell you, things are far more complicated, and the number of reactions that happens in the atmosphere can run into thousands. Okay, and some people who try to understand the system, they want to model it, because you see why we model the things, because it's impossible for us to measure everything. It's impossible for us to have such a system that can measure everything, whereas if you can model it, you can model it everything as function of time, how the things are changing, what will happen at 9 o'clock, what will happen at 9:15, and what will happen in the evening 5 o'clock. So we can model it. So, but basic things which are the important things that we will discuss in this course at some point or other are these things that we'll discuss. Ozone, we understand. So sources, as I've been repeating again and again, in troposphere, ozone is always a secondary pollutant. So ozone is not generated from the primary sources. You will not find ozone by and large from any chimney that it comes out. It is formed in the atmosphere. And who is the main player? Okay, the impact is UV. Of course, this is UV protection. But then for the ozone formation, again, what is important is UV, that we'll see probably today in the class. We also have methane emission. Generally, again, methane is not so much emitted by our industrial processes. By and large, not so much. but then we have the wetlands, we have the the animals, and there could be leakages, animal waste that will produce methane constantly through the biodegradation. You all know about that. Methane is a very serious greenhouse gas. How many times more greenhouse impact, how many times more potential than CO2? 16 times, yes, that's correct. 16 times has higher potential than the CO2.
Sir, what is the pipeline losses indicate?
See, the methane is that gas which is transported, CNG, so there could be leakages, right? Because we have the CNG is a big way now, right? And the methane is transported from lots of places from one end to another one, so there could be leakages, that is the pipe losses. Okay. We also have the NOx problem that I discussed with you. Again, let's quickly take recap. What is NOx? NO plus NO2. What is largely at source, at the emission source? NO. And what is largely in the atmosphere, what do we breathe? NO2. Very good. Okay. We also have the CO that is formed, that's fine, toxic, and it also, you see, again and again you will see that OH thing appearing here. So we should see that how OH will play a very significant role. Of course, OH again is not as a thing which is emitted from the source, it is formed in the atmosphere, and we all know, even from our water chemistry, OH is hugely reactive, okay, and its concentrations are very low actually. Sometimes you will wonder what are the units we normally measure the OH in. Moles per liter the concentration will be very low, 0.0000 something. It is interestingly sometimes can be measured in number of molecules, for example, 10 to the power 12 molecules per liter. So that is low concentration, but the role which it plays is very vital. Okay, so CFC, we all know about the CFC business, and then ozone photolysis. In fact, some ozone is formed, okay, and then the OH is again formed from the ozone synthesis, we'll see, but this can also clean the atmosphere, so there are positive things that will become more clear to you. VOCs, volatile organic compounds, okay, sources fuel this thing, and then they are also, it's very funny that you see here that this can also lead to formation of ozone, and we'll see. It sounds very funny, but then it can also lead to from the ozone. SO2, again fuel combustion, volcanoes, aerosol formation, okay, heterogeneous chemistry, and this can also lead to acid rain, if you recall the impact of SO2. But you see, the interesting part is that SO2 can also be responsible for aerosol formation. So if you want to control aerosol, okay, you not only need to control the aerosol at the source, but maybe you need to control SO2 as well, okay. So SO2 control will not be determined by the SO2 concentration in the ambient air for the people to breathe. SO2 concentration may be in the emission, may be controlled or regulated by the particulates that we need there. So look at the complexity of the thing, and some of the things we'll learn. And NOx similarly, HNO3 is the sole, almost sole source of HNO3 in the atmosphere is from the NOx reaction. Some of the HNO3 is released from the nitric acid plants also, okay, but that is not so this thing, because that will be a very local phenomena. Ammonia is very interesting pollutant, a very interesting pollutant. Again, this comes from the livestock, okay. How from the livestock? How ammonia will come from the livestock? Waste degradation and things like that. And the fertilizers, like the moment you use urea, some of the ammonia can escape from there. And then this interesting part with ammonia is that they can neutralize both HNO3 and sulfuric acid, but they also add to the formation of particles. How? H2SO4 and ammonia. What will it form? Ammonium sulfate. Ammonium sulfate are the particles. H2SO4 was in the vapor phase or in the mist form. This was in the gaseous phase, and then what you got as a result in the atmosphere is a particulate pollution. So that's a little tricky there, ammonia issue. So this will little give you the idea. Let's get into the chemistry now, and well, this is something we all know. I mean, I've talked about this. The source, transport, reaction, transport, and then there has to be sinks. Sink has to be, well, that's how the things get out of the system. If there were no sinks, these pollutant levels and the secondary pollutant will continue to rise. Okay, there will be endless thing, and then the survival of the people and the things will completely stop. So this is very important to understand the sinks also. But let's get into some more specific things. Okay, that is, atmosphere can also be a catalyst that I told you. Did I give you an example of how SO2 was formed to H2SO4? Yes. Anyone remember how sulfuric acid is produced in the sulfuric acid plant? No, it doesn't matter if you don't remember. But what we do is we take the sulfur, burn it, make sulfur dioxide, then oxidize SO2 to SO3. Okay, that is what is this. And then once we oxidize to SO3, how do we oxidize? It is a catalytic oxidation of SO2 to SO3. Conversion of SO2 to SO3 is not easy. Okay, so in the sulfuric acid plant, once you are producing SO2, okay, you supply oxygen, no doubt about it, but provide, okay, a catalyst. I don't know now if you can recall, vanadium pentoxide is a catalyst to oxidize SO2 into SO3. Okay, you need to balance this, of course, which you can do. Okay, and then so once you have this SO3, okay, plus SO3 is reacted with water or absorbed in the water, and you get, and this is what I mean is as a catalyst. Almost identical reactions can occur in the atmosphere. Okay, because you have the SO2, okay, levels will be extremely low. You have the SO2, you may also have the catalyst present in the atmosphere, that is vanadium pentoxide. Where does the vanadium come from? Well, there could be many sources, but almost all diesel, okay, almost all diesel or the fuel oil, okay, it contains a vanadium, because it is all extracted from the ground. The vanadium goes in there, and vanadium, I don't know what is the atomic weight of molecule vanadium, any idea? It must be pretty heavy, I'm not sure. I mean, but it's heavy, so when you do the distillation, okay, the vanadium continues to be at the lower end. It doesn't go out and doesn't appear this thing. So you have the fuel oil, the furnace oil, the vanadium will be there. Vanadium will find the source in the atmosphere. SO2, this is one of the routes. There are many other ways you can form the sulfuric acid. So the catalysts play an important role, and our atmosphere is oxidizing in nature because we have lots of oxygen there, right? And what else? This is one route that. So role of the catalyst cannot be undermined. Okay, so that's what is being seen. So just gave you a little example that how sulfuric acid could be formed. There are other ways also for sulfuric acid to be formed, but one of the important thing is the oxidation to SO3 and then to react with water. And this reaction is almost instant. Okay, SO3 is more or less unstable. It quickly wants to react. Okay. All right. That is again reaction, the reservoir, what is happening. Now, this slide we don't want to keep for long. You all know about this, that well, there is a combustion of the fossil fuel and biofuels, cars, heating, industry, forest, and this so on are burning. That also, you see, there is a lot of work onto the natural forest fire, and that also produces a lot of trace compounds. Leakages and evaporation that we have discussed. Agriculture, as sometimes you just wonder as to why agriculture. Agriculture can be a serious source of emissions of not only the dust with the tractor and the people working, but also they are spreading the urea, so ammonia comes out, you are spreading the pesticide, and many of the pesticides are volatile, and as a result you are heavily spreading it out. I don't know if you were there in Anubha's presentation, and then things can be volatile, and you're putting it onto the floor, in the field, and then it can just become volatile, and then it can again make the particulate, or it can stay in volatile phase. So agriculture, people, this is the latest thing people are talking a great deal about, the air emissions and air pollution from the agricultural activities. Plants and soil can also sometimes give out this thing, volcanoes, oceans, okay, atmospheric chemical reactions. So there can be source of the trace compounds that we get. But let's see some of the major issues. Okay, so we need to quickly take the recap of the chemistry part. You have done it all, but we'll have a very simple reactions to recap the things. We all know the gas phase reactions can happen between two compounds, and these things, they are more reversible thing. You can write it in this form, and then this. What is M? What else it can be? Okay, that is one part. What else it can be? See what happens when you're having some reactions, okay? Then a lot of energy that is created, okay? Vibrational energy, the temperature energy. So somebody should be there to absorb that energy, okay? And that part is generally largely done by nitrogen and oxygen. So we should not forget that some energy comes out, okay? And suppose the reaction was, let me tell you, for example, if the reaction was A plus B equals to C plus D plus heat, okay? Okay, let's talk about that. Reversible reaction, C plus D is heat. For example, this thing can happen, right? Most of our reactions are oxidizing in nature. So what will happen if the heat is there, okay? If I don't remove the heat, then what can happen? Reverse reaction, yes. So C plus D is being formed, okay? And then suppose there is no one to take care of the heat, it might just go back, okay? So what we are assuming is that for this reaction, which might happen sometimes, we also can have, like, this is one kind of energy, there could be another kind of the energies which can be there. So there should be someone to absorb the energies, or there can be, and it can be catalyst as well, okay? Good.
So M will be some chemical or something like that?
M will be some chemical, some gas, something that can absorb, okay? For example, nitrogen, the oxygen largely, that doesn't change so much in composition, but they are able to absorb the energy. Okay, let's, what is the difference? Somebody tell me, what is the difference in homogeneous and heterogeneous reactions?
They happen in the same phase.
Same phase, that is a key word. So gas versus gas is a homogeneous reaction. Liquid versus liquid is homogeneous. Solid versus solid is homogeneous, and then the heterogeneous. So we should all understand that, well, there could be different kind of this thing, and then it could be heterogeneous, it could be surface reactions, it could be the bulk reaction where the things are meshing into the another one and the reactions can happen. This little, what you will recall that you have done it all in your high school, but still we need to have a look onto this one. Okay, think of the reaction, okay, A plus B plus C plus D, and then I can write the rate of change of the concentrations of the compound with time. And fortunately here all coefficients are 1, right? So you can write the rate of change will be dA will be equal, or decrease in dA will be equal to decrease in dB, and that will be equal to decrease in dC? Increase in dC. Okay, alright. You are following. Okay, so then you can dC and dt is the one which will be on the plus side, as you can see. And we'll use this concept, and then also these reactions and the real concentrations of A, B, C and D will depend on the largely onto the, recall, rate constant, equilibrium constant, and that sort of thing. You all know about that. What if the coefficient was not 1? See here the coefficient is 1 here, 1A, 1B, 1C, 1D.
The rates are different for different
But how do we write that?
So for example,
Square, sir.
for example, the reaction is 2.
No, I'm just talking about this one only. The rate of, I'm not talking about the final concentration. Rate of change of A, B, C, D.
So if the number of moles are larger than 1, then the rate is decreasing for that reactant.
So 1 by A, dA dt equals to 1 by B minus, of course, dB dt equals to 1 by C, dC dt 1 by D dt. Okay, don't forget that. So all your little thing what you've done before. In general, I'm saying the change in the C. Okay, C where here will depend on to the how much is the quantity I have in terms of A and B times the rate constant. You all know about that. Okay. K is called the reaction rate constant or rate constant. K often depends on to the temperature and the pressure. What are the units of K?
1 second.
So depend upon the type of
Absolutely.
order of reaction.
Order of the reaction and the products you have, order of the reaction basically. So it's not per se. That was the reason I asked you. Little fundamentals, but we need to be very clear about these things. Okay, and we will utilize this very quickly as we go by. And okay, so we'll apply some of these concepts. Okay, and so we also need to understand a little bit about the quasi or pseudo steady state situation, and that will become clear to you about the steady state. For example, the several reactions proceed via the formation of an activated complex, and that decides what is going to happen, which needs to get rid of the excess energy in order to stabilize or quenching of this one. For example, O plus O2, you have an acid oxygen, it can form in the excited state ozone. It must shed off the energy to someone to become at the ground state. Okay, the rate of equation for the intermediate complexes is given by now you see here what I am trying to write is the rate of change of concentration of O3 in the excited state. Okay, so we have to see in what way O3 is formed, which reaction is forming the O3 in the excited state, this one or this one? The first one, because this is the product. Okay, and here I am destroying it. Okay, so write the concentration in terms of the change in the concentration. Okay, that is input minus output, that is a change. Okay, this is input. If I am saying K1 O times O2 minus K1 O3, why this?
So it is reversible reaction.
Reversible reaction, right? This can also go this way, right? Fair enough. Plus or minus, I don't know. Again minus. Again, this reaction also will destroy the reaction. So you should learn these little simple things. You need to learn that how you can write these equations. Okay, simple things, but it gives you big results. Okay, so that you can write here, and then the lifetime of the complex 3 is sufficiently short. Okay, then it can be called pseudo steady state. Okay, it's being formed and it's being destroyed. Okay. Okay, so in that case, if I can take this equals to 0, then I can find out what will be the ozone concentration in the excited state. Does it mean something is being destroyed quickly and something is being, like rate of generation and rate of destruction is the same? Does it mean the concentration is 0? No, that's a very important thing. Concentration is time independent or time invariant. Right? Is the statement okay? Concentration is not changing with time, but it has concentration. Right? So those things which are quickly destroyed and the same rate is being produced, same rate they are being destroyed, is what we take that assumption, and that is called as a quasi or pseudo steady state. And that's what we apply the concept of pseudo steady state, and then you can find out the concentration. Look, we understand the reaction, and if we need to know this concentration with little knowledge of chemistry, that we will be able to say in the atmosphere what is happening. Okay? Any question?
Sir, this like concentration and time dependence. Sir, this relation is only for short duration reactions.
for any reaction.
So, but suppose sir, if we take plot of concentration versus time, like it would be changing per unit time, or like changing, increasing or decreasing with time.
If that is the case, your function, the function will be, should represent that. T concentration, like in mostly water pollution, air pollution, we say things steady state, things decrease with first order reaction, so it can go like this. Okay, so then you are writing simply all you know about that is, right? Okay, suppose this was like this. Okay, then obviously the dc dt, the function of this curve will be different. That's all it need to be. But it may not be very easy to write function, that is a different thing. Okay, but then you should be able to write dc by dt is constant and some function of ct, that's correct. Right? That's all you need to do. Okay, and don't forget that we all referring is moles per volume. Okay, moles to specify this thing in the moles is there. So there's a little chemistry that we talked about, and so let's try, and then we go to a real problem. Okay, with this background. Okay. Most of the reactions that we'll discuss will be driven by the photodissociation, and photodissociation is very simple. Photodissociation means you have the UV, that is energy, and that's able to break the things. Okay, in simple terms, the energy of a photon absorbed by an atmosphere molecule is transformed to the breaking of a chemical bond, so that the molecules are dissociated. Okay, and form something else. For most molecules, photodissociation requires radiation in the UV range, that's below 380, and molecular photodissociation requires radiation in the UV range. So the sunlight, it stops some UV radiation, but some UV radiation still reaches us. Okay, and that is what will trigger many of the reactions. You all know about that where the energy issues are there, and how the energy and the wavelength related. More energy. There? Are you sure? Or okay, inversely. Or if I take in terms of frequency? And what is the constant of proportion? Planck's constant. Okay. But what happens is, this is where most of our atmospheric photooxidation or photodissociation takes place with the help of this visible range, and that too largely less than 380 nanometer. Okay. What we will do is, while we have the time, let's do this one. Okay, for example, if you have ozone, okay, for this thing, H you can break down to O plus O2. It can be broken down by the two different wavelengths, and then it can produce O plus O2. This O can be in the ground state, and if you have this thing O can be in the excited state. Okay, so you see here, if I have shown here, this O is what in the ground state, right? From here you see O and O. This O can react with oxygen to bring back the ozone to you. Okay, but if it is in excited state, because with this tonometer, if it is in excited state, okay, do you see this reaction is reversible or non-reversible? It's non-reversible. Okay, so I can never get back ozone. If from this route, if my energy is coming in this range or this nanometer, you see here, once I get this thing, okay, I'm not going back to ozone. Very interesting thing. Okay, and you have to observe that and keep in mind. Okay, unfortunately you have to understand only, I mean, we are not getting a great deal in this thing. So there must be somebody to react with the excited ozone. Formation is important for the formation of OH radicals. You recall in the beginning of this class, I was emphasizing OH, 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 and really OH is very, very important. And I'm just giving you a little idea where the OH is coming from. There are other sources of OH as well, we'll see. But you see here, the OH came, okay, it can react with the water vapor in the atmosphere, and in the conditions of the humidity, temperature, that what we get in the atmosphere. So we can get the OH radicals. When do you think the OH radicals will be high in the atmosphere? In the daytime, when we have lots of H news, right? Okay. So here you get you can make the OH radicals here. Okay, no problem there. So quickly tell me, okay, where is the energy more, here or here? 320. So if energy is more, I'm likely to get more excited, more OH radicals. That's what it is. Okay, energy is more, and then also it depends on the temperature. Why temperature is more, then you have higher this one. Why? Because the energy will be higher at the high temperature. Body radiates at the higher temperature than it will radiate more in the smaller range, right, if you all recall. So this is what is the thing, that O1, this thing. So you have the higher temperatures in the daytime, and then you will have the more O1, the excited atomic oxygen, and then you will get more and more of OH. Okay, and so therefore what I can tell you is a chemistry or atmospheric chemistry will be different for us, it will be different for America, it will be different for for example Norway. Okay, because we get, our temperatures are high, and so our radiation, our H news will be more, and our chemistry will be entirely different. So we need to study the chemistry and the science, okay, and then apply to a local condition. Always remember, the science is universal, whereas the application of science is local or regional. Interesting statement, that science is universal, but the application of the science, okay, is regional or local. Okay, so you see here, our things in India, for example, will be very, very different than what can happen, which is very evident because H news will be different, that what we are getting the energy, and so there will be variation between winter and summer. Okay, there could be variation in the monsoon period when you have lots of overcast conditions. Okay, so unless we know the science, okay, we won't be able to tell what is happening to ozone, what is happening to the OH radicals. Okay, let's go down.
So in the same ozone, it is splitted to oxidation.
Excited oxygen and the ground, depending on the radiations that you are getting. Okay, it can, both routes can happen. The first route, this ground oxygen can react back with the oxygen to produce ozone again. Okay, when it is producing ozone again, then it is a kind of null situation. Nothing is happening basically. Production, destruction, production, destruction. But in the second route, where you have the more energy with less than 320 nanometers wavelength, it breaks to ozone, which is the excited state, plus O2, and this excited atomic oxygen and O2 will not react to produce ozone back. So this one become, somebody should take on to that. Who takes on is, the water is one of the things, the other can also take, and that will produce OH radical. In fact, one atomic oxygen molecule in excited state will produce 2 moles or 2 molecules of OH. Okay. All right. Any question? Okay. Then let's proceed. And we are talking the same thing, pseudo-steady state for excited state of O1D. Now I'm not using K's, I'm writing with J. Many books use J. Quickly see from the notes the earlier figure and make sure that I have written here correctly. Just spend about, let's say, 10 seconds, and then let's see if I have written correctly or maybe wrongly.
Reversible reaction.
Reversible reaction, for what I need is O1D. Was any reaction reversible for O1D? No. So it can react and react with water and get destroyed, O1D, right? And O1D can also destroyed by this route. Okay. So again, pseudo-steady state, put this equal to 0. You can even find that what will be the concentration of excited atomic oxygen given the ozone concentration, okay, given this concentration of this and this, and sometimes this we take as a constant, okay, and can be taken as a constant, and then you see that you can find out this equation will not be so easy to solve because you also have this in here, okay. It's not a simple equation to solve, okay, right? Okay, but you can solve this one and then this thing. Now I want to come to the real atmosphere. That was so far the background part of it. Pay attention. Now the idea of showing this one is not that we can go a little fast. Okay, this is what is happening really in the atmosphere. Okay, we know that we are getting a lot of NO2. Where the NO2 has come? NO2 has essentially come from NO. Okay, NO2 it is very photosensitive, more than most of the compounds. Okay, so the kind of this is the range which is not filtered by the ozone layer and still reaches the ground. Okay, because ozone layer is not filtering all UV radiation, right? Maybe you'll recall that it can stop some, but it cannot stop some. So this thing can reach this kind of energy, this kind of photon can reach, and then this is specifically sensitive to this thing, and then this can be broken down to NO plus O. Okay, this O, okay, can react with O2 to form the ozone. Okay, what is this O? Tell me, is it excited states or it's a ground state? Ground state. Okay, because then only it can react with O2, if you recall this thing, and then produce ozone. Okay, this is basically equation 1 and 2. Okay, are the fundamental equations to form the ozone in the atmosphere. Okay, we are talking a great deal. Atmosphere means, I beg your pardon. Don't forget that we are discussing now troposphere. We are not in the stratosphere. We are not in the stratosphere. We are all don't miss me on that point, because we are talking just about the troposphere and not about the stratosphere or the higher atmospheres. So this is the basic fundamental equation. Okay, that's how you will constantly get ozone from here. Okay, M, which is N2, ρ2 are the another molecules that absorb the excess vibrational energy and thereby stabilizes the ozone molecule that's formed. There are no significant sources of ozone in the troposphere, that's again and again. So by and large, whatever ozone is formed in the troposphere is governed by equation by 2. Okay, by equation 2. Okay, and I would add, I'll agree with this one, and largely with equation 1, because almost no other photochemical reaction produces the ground state oxygen. So see what a fantastic or some fundamental role played by NO2. Okay, so and then this becomes very vital and this becomes very basic unit. So equation 1 and 2 are very important. So let's write the chemistry, and whatever we have learnt, we'll try to build a model on this one. Okay, let's try to build the model. Now apart from this, let's not forget, we may also have the NO in the atmosphere. We have, of course, we have the power plants, we have the automobiles running in and out, so we have NO there, and this can also react with ozone to form the NO2 and back to oxygen. Okay, this NO2 is again available, this one, so it's more like, appears to be more like the closed things, and it might be a steady state situation. Okay. Let's write the chemistry and kinetics about this one. Let's write about NO2. Okay, where is NO2 formed? First talk about the losses of NO2. dC by dt equals to minus Kc. We environmental engineers understand this thing, fundamentally, like dC by dt equals to minus Kc. So something like dC by dt is minus Kc. That is loss. Observe, if also the NO2 is NO2 being formed from reaction 3, K3, okay, who is forming it? Ozone and NO, their product. Simple. Okay. Keep this one there. Okay. Now I can write from the nascent or atomic oxygen which is at the ground state. Can you see that how it is being formed? It is being formed by the breaking of NO2 plus reaction constant is K1 NO2. Where it is disappearing, okay, it is forming ozone reaction 2 K2. Simple. Okay. Let's proceed further. The oxygen atom is so reactive that it disappears by reaction 2 virtually as fast as it is formed by reaction 1. Okay. So what situation we are getting into? Quasi or pseudo steady state. Okay. So we are getting in that situation. So in dealing with the highly reactive species such as the oxygen atom, it is customary, okay, which is reasonable thing to do, invoke the pseudo steady state constant. So then if it is steady state, it means the change in concentration with time is 0. So you can find out what will be the concentration of O, which will depend on K1, K2, NO2 and oxygen. Isn't that thing we have done fantastic thing that we just need to measure NO2 and NO, and we might be able to say something about ozone, right? And how much is ozone will form. And if I also want to have you made some mistake here? Oh, I'm sorry, we are still dealing with O. Okay, that will come in the next tab. We haven't talked about ozone, by the way, my mistake. Okay, equation 4, okay, at the steady state. Okay, what was equation 4? I didn't look at the screen and I kind of went ahead. Equation 4 at steady state. Okay, at steady state this becomes 0. Okay, O3 will be something very simply K1 times NO2 by K3 NO, right? So that is what is written. Ozone K1 K3 NO2 NO. Okay, and then this is steady state concentration ozone. Concentration is proportional to the ratio of NO2 to NO because K1 K3 will be another constant. Okay, we now need to compute NO2 and NO, and now we have to get the NO2 and NO, and now we will do little work as to modify this model. This is this concentration at what time? This concentration at the steady state, right? At the current condition when we are assuming steady state. But let's model it. Okay, how things can happen with time, and if we start with some initial concentration. See, things have to trigger. You have to have something happening. Okay, then you get to the situation. So since we have developed the models, so we'll use the model to say what are the concentration with time and what are the other steady state concentration, and what will happen to NO and what will happen to NO2. So what we are saying here is, suppose we are now starting with this one, then what we are saying is, let's say to start with, okay, at time t equal to 0, NO was 0, NO2 was some concentration 0, ozone was some concentration 0. Okay, so we are like more or less we are taking like a big chamber, and in the chamber we started the reaction and start observing them. So we have NO 0, NO2 0 and ozone 0. Initial concentrations or initial levels. Okay. Then you need to solve this one. Okay. This is what we had already written, right? Okay. But then quickly there are some conditions that we need to take. Let's go down there. Okay. I need certain informations. Okay. Nitrogen has to be balanced. Okay. NO plus NO2, because they are not the NO nitrogen is either in the form of NO or in the form of NO2. It's not nitrate, right? It is not N2O5 or something. So it means mass conservation. This should be true. Okay. You can also see that ozone, that is change in the ozone, okay, will totally depend completely on change in the nitrogen species, right, nitrogen species. So with this knowledge, okay, we can solve the equation. As a result, you can find out the ozone. It all depends, like at steady state, no doubt about it, but this is what is the initial concentration you started with, okay. It is steady state. Don't forget that we have invoked steady state conditions, but we started with this picture. And what is that picture? At the steady state, that you can solve this one with the information we have. Try to do this one, okay, try to do this one, because this is important. I mean, it takes a little while, it is not very straightforward, but then it's basically algebra, nothing more than the algebra, okay. So you see here, with all this knowledge we had, I can now, depending on the suppose the Kanpur basin I can see early in the morning what is the emission of NO, what was the NO2, what was the ozone if it was there, and I can try to predict the ozone concentration at steady state, okay. So this is. Suppose there was no initial ozone or NO, no NO was there, okay, then this will reduce to this, okay. You can see that again, simple algebra again. What if I had no NO2, okay, and I had no NO? What should happen? If there is no NO, NO2 cannot be formed, we know from the, and if there is no NO2, can ozone be formed? Ozone cannot be formed, okay, because only way the ozone can be formed, remember, is the photo dissociation of NO2 in the range of H nu, which was less than 435 or something. So if you put NO2 equals to 0 in this model, this is already 0 I am taking, okay. So you put this NO2, what is ozone concentration? 0. So this what is the fundamental thing, okay. So this modeling was done. So let's have a look at the results of the model, okay. People run the model and things like that, okay. They took 0.1 as NO2 at the initial stage. No NO was taken, because we know that from NO2 it will be formed. And then what is the ozone concentration that was predicted from the model? 0.027, as with 1 it was produced at the 0.095, okay. No theory, no science is complete without having tested it on the field. This is all we did from more or less from the theory. When the people went out and measured, when they had such kind of concentration in the atmosphere, not a controlled situation like this, okay, they had such a situation in the atmosphere, they knew, and what the ozone levels what they got were way high, and then the numbers you getting there. So in a way, I'm sorry to say that model failed, okay. We did all our science, and the failure is a as I would say, is the step towards the right direction, towards the future research. If you fail with your theory, you don't have to be disappointed. It certainly tells you that you have not understood the process, okay. Having done everything, but you see here, I don't know what is written here, but we can read, the concentration of ozone attained in the urban and regional atmosphere were often greater than those sample calculations from the model, as you see here. Since most of the NOx emitted is form of the NO and not NO2, the concentration of ozone observed can be calculated accurately if the reaction governed by the equation 1,3 only. It must be concluded that the reaction other than 1,3, something more is happening which we have not thought of, okay. And this whole thing was given by a scientist called two person, Hagen and Smith, great people. They kept on publishing after 1952 lots of great papers on this field. So what we'll do is we'll stop here and try to answer the question as to why our model failed. and how we can rectify the model, and we should be able to, if these people come in 1952, they can give some answers. We should be able to, at least able to say what are the ozone that will be formed here. Okay, stop there, and you should get these slides. I'm sure Bera will do something about it. Okay, stop. Thank you very much.